Here we have question B3. It's looking at momentum, energy, and power. It's obviously from Unit 2, so you need to have your data booklet open there. Obviously, the formulas that we're going to be looking at here are this one over here, your momentum, your energy formulas, all of these ones over here. So you should have these available over here. These could all come in at some point or other. Obviously, also you're looking at your conservation of momentum, conservation of energy, your definitions in terms of power. All these things will be necessary. But to help you get on your way with this, often these first questions, these definitions also are useful. So they get you thinking in what's going to be coming up. So in this Principia Mathematica, Newton expresses third law of motion as to every action there's always opposed and equal reaction. State what Newton meant by this law. So often use an example. So I would say if you have, I don't want to write this all out, but if you have an object A exerts a force on object B, then object B will exert an equal force but in the opposite direction on object A. There you are being very clear in explaining it, and that it would be 1 mark. So make sure that you are clear and that you put the thought over that it cannot be looked at in different ways. Then it says a book is released from rest and falls towards the surface of the earth. So we're looking at that part of it, falling towards the surface of the earth. Discuss how the conservation of momentum applies in the earth book system. Now we have a conservation of momentum. That means that the total momentum of the earth, the P total for the earth and the book, will be constant. So as the momentum for the book increases in one direction, we're going to have the momentum of the earth will be increasing by the same amount in the other direction. So we have this earth book system, you see. We have that system, and the total momentum of both the book and the earth will remain constant in that whole time. So can you put that in writing, in a form of writing? It's difficult for me to always write this with this pen, and also I don't want to take up too much time. Good. Let's go over the page then to our next question. So here we have this question here, and let's read this really carefully. It says a large swinging ball is used to drive a horizontal spike into a vertical wall. The center of the ball falls through a vertical distance of 1.6 meters before striking the spike in the position shown. The mass of the ball is 3.5 kilograms and that of the spike is 0.8 kilograms. Immediately after striking the spike, the ball and the spike move together. Show that the speed of the ball on striking the spike is 5.6. Alright, so let's have a look at that part. So it's going to fall down. This falls down like that, and as it falls, it obviously speeds up. You're getting a change of potential energy. Your EP there will equal your kinetic energy there. So your EP, your potential energy, is given by that, and your EK is given by that, and those two things are going to be equal. So we're going to get a half mv squared is equal to mgh, and as you can see from that, we can actually cancel out our m's. They cancel out, and we get our v is equal to 2gh. V squared we equal that, and to find our v, we'd have to take the square root of that. So it's going to be 2 times 9.81 times our height that it falls, 1.6, and we've got to find the square root of that. And when you do that, you should get a value of 5.6 meters per second. Now, in the second part here, it says that the energy dissipated as a result of the collision. Now, this is the collision that it's speaking of here, about striking the spike, and it says they both move together. So what fact are we going to use for this? Well, it says that your energy dissipated, your energy lost, is going to be 10 joules. But what will be conserved? It will be your momentum. Now, you know that this is talking about momentum. So momentum before is equal to the momentum after. So what was your momentum before striking? Well, it's going to be your m, 3.5 times your 5.6, and that's going to equal your momentum afterwards. Now they go off together, so can we see that that would be equal to, they're moving off as a system now, 3.5 plus 0.8 times your new velocity. And when we work that out, we find that this velocity equals about 4.6 meters per second to the negative 1. So your EK before EKB is equal to a half 3.5 times the 5.6 squared, and your EK afterwards, that works out anyway, work that out. I will have a look at that now. And your EK afterwards is going to equal a half. Now we're going to have this value over here. It's a total energy of that is 4.3 times 4.6 squared. And the lost energy will be the subtraction of the two from the one to the other, and you'll get about 10 joules difference when you do the two. When you this one over here, you subtract your EK before minus your EK afterwards, and you'll get about 10 joules. So whenever you're getting a collision, you can apply for all the things that are happening in the collision, so between these two things, your conservation of momentum. Sometimes when energy is conserved, then you have got what we call an elastic collision, and where energy is not conserved, as we have in this case, you have an inelastic collision. Okay, good, so we've got that done. Now let's just move on to the next point. It says, as a result of the ball striking the spike is driven in 7.3 times 10 to the negative 2 meters into the wall. Calculate, assuming it to be constant, the frictional force F between the spike and the wall. So the wall has to do a certain amount of work on the spike ball combination to cause it to slow down. So we have work is equal to force times distance. Now this work would be all the energy that it had, and that is going to be the energy that it had, so that equals the value that we worked out, your half times 4.3 times 4.6 squared. That is the energy that it's got is in the form of kinetic energy, and that's equal to your force, and we're going to have to divide that by the distance, because we divide that by 7.3 times 10 to the negative 2 meters, and we get a value there of about 6.2 times 10 to the 2 times 10 to the 2 newtons. They may have actually, I've taken that answer directly from the answer. I think there may have been a mistake. If there's a number out there, don't worry about it. But notice here, what's very important is that you give your answer in two significant figures, because the smallest number of significant figures is 2. Then finally it says the machine that is used to raise the ball has a useful power of 18 watts. So power is equal to 18 watts. How long does it take for the machine to raise the ball a height of 1.6 meters? Now the work to raise it 1.6 meters would be all the potential energy that it gets, which is mgh. So we have for that the mass is, so that would be equal mgh. So the mass of that is 3.5 times your 1.6 meters times your g, which is 9.81. And you get that. Now power is equal to work over time. So if I put this in here, then I have got my time is equal to my work divided by my power. So I'm going to take this value over here and put it into my work, and I'm going to take my 18, so that's going to go into there, and then I'm going to divide it by 18, and you should get about 3.1 seconds. Again, two significant figures in your answer.